In this section, we're going to be looking at molecular orbital theory. By the end of the section, you should be able to outline the basic quantum mechanical approach to deriving molecular orbitals from atomic orbitals, describe traits of bonding and anti-bonding molecular orbitals, calculate bond orders based on molecular electronic configurations, write molecular electron configurations for first and second row diatomic molecules, and relate these electron configurations to the molecule's stability and magnetic properties. One of the reasons we need molecular orbital theory as opposed to the others that we've already discussed is because of paramagnetism, which is when something is attracted to a magnetic field, and this is caused by unpaired electrons. So pause this video and watch the YouTube video I have linked on your account that shows the paramagnetism of oxygen. According to the Lewis structure, oxygen has no unpaired electrons. However, experiments show it has 2 unpaired electrons. So something must be wrong with the Lewis structure that we have. Molecular orbital theory is able to explain the paramagnetism of oxygen, as well as other molecular structures that are beyond the scope of this class. It uses combinations of atomic orbitals to produce molecular orbitals that are delocalized over the entire molecule, instead of having those electrons localized over the 2 atoms that the bond is describing. This chart here shows a comparison between valence bond theory and molecular orbital theory. So valence bond theory considers bonds as localized between one pair of atoms that the bond is discussing, whereas molecular orbital theory considers the electrons delocalized throughout the entire molecule. In valence bond theory, we have overlap of atomic orbitals and hybrid orbitals that form sigma or pi bonds. In molecular orbital theory, we combine atomic orbitals to form molecular orbitals, sigma, sigma star, pi, and pi star, which create bonding and anti-bonding interactions based on which orbitals are filled. Valence bond theory predicts the molecular shape based on the number of regions of electron density, whereas molecular orbital theory predicts the arrangement of electrons within the molecule. In valence bond theory, we need multiple structures in order to describe resonance. So in molecular orbital theory, we have 2 orbitals that are going to overlap. And we need to remember that electrons can be described as waves, not just particles. So if we look at the wave functions for those orbitals, those 2 waves can either combine constructively or destructively. If they combine constructively, then we have a bonding orbital. If they combine destructively, then we have a node in that internuclear area for a sigma bond, and we end up with anti-bonding. So I have 2 s orbitals that can combine, and they can either combine with constructive interference to produce a bonding orbital called sigma s, which has lower energy, or they can combine through destructive interference to produce an anti-bonding orbital, sigma star s, which has a higher energy. The same thing can happen with p orbitals when they overlap to form sigma and pi bonds. Now we have the 2 lobes for the p orbitals, so we end up using colors to show whether they're going to do constructive or destructive interference. So we can have a sigma p for the sigma bond from p orbitals overlapping, forming constructive or again destructive interference. And again, the sigma star has the node in that internuclear area. We can also form pi bonds that are molecular. And again, those have to form specifically from p orbitals. So the p orbitals, if they undergo constructive interference, those 2 pink lobes are lining up, the 2 blue lobes are lining up, we end up with a pi bond. However, if they are out of phase and I have destructive interference with red on one side and blue from the other one on the same side, I end up with a pi p star, which is an antibonding orbital, which has another node that goes along where that overlap usually occurs for the bond. Now I'm going to have two p orbitals that can overlap to form the pi bond, which means I am going to be forming degenerate molecular orbitals. I'm going to form 2 pi and 2 pi star orbitals. So when that happens, remember, since they're degenerate, they have the same amount of energy. So just like when we were forming atomic electron configurations and put one in each degenerate orbital before doubling up, the same thing is going to happen with my molecular orbitals. So when I'm looking at molecular orbitals, I'm going to have the s orbitals, constructive interference forming the sigma s, destructive interference creating the sigma s star. And then I have the p orbitals overlapping that are going to form the pi px constructive, and then the destructive interference forming the pi px star antibonding. And then we're also going to form two constructive pi orbitals, pi orbitals, and two from destructive pi star orbitals. So when I end up combining all of these orbitals, the molecular orbitals I get one sigma s bonding, one sigma s antibonding, one sigma p bonding, one sigma p antibonding, then two pi p bonding, and two pi p antibonding orbitals.